All right, so pre-calculus 20, we're taking a look at a chapter 9 review here. And the chapter 9 is about linear and quadratic inequalities. So obviously linear is a straight line. Quadratic is some kind of parabola, right? Either facing up or facing down. And an inequality is different than an equality. An equality is an equation, and in an equality, we're looking for the points that are on the line, right? But an inequality is we're looking for points that either are greater than the line or less than the line. And in some cases, also including the line. So the solution region for, let's say, in this example that we have on the screen here, ax plus by is greater than c. This is the equation, the boundary line, which we always try and graph first or find first. And then all of the points on one side of the boundary line will either be greater than or less than the points that exist on the line. And so this is an example of a solution region where this boundary line, we use the terms in this boundary line, but all of the points in the blue region satisfy this inequality, where if I take any point and I put the x value here and the y value here, then this side will always be greater than this constant over here. And all of the points will satisfy this inequality. Therefore, it's called a solution region, okay, or a solution set of points. Down here, all of the points in this region, so let's say this point right here, maybe this is 5, 0, or whatever. So this point would satisfy this inequality. It's part of this solution region. If I put 5 in here, and if I put a 0 in here, and then I evaluated the left side, it would be less than this constant over here. Okay? So we have three parts to these inequalities. We have the boundary, and the boundary is either a line or a parabola, which we'll talk about later. And we have the solution region that would be above or to the left of that boundary line, and below or to the right of the boundary line. And those would satisfy different inequalities. And of course, the test point here, that's like this 0.50 that I tested in the inequality to make sure that this is part of the solution region. Any questions there about that? This should be just review, but if you have any questions, please let me know. Class, okay? All right, here's another thing I need to talk about, of course. If we have a less than or equal to sign or a greater than or equal to, that means that the boundary line or the boundary is included in the solution region. That's the or equal to. And that will show up as a solid boundary line. Okay, so the line will be a solid line. And that means that the points that are on the line are included in the solution region. If the inequality does not have an or equal to, like these ones over here, it does not have an or equal to, then that's when the line is dotted or dashed. Okay, so notice in this example, there's no or equal to. Therefore, this line is a dashed line, meaning it's just a boundary. The points on that line are not included in the solution region. Okay, so that's the basic premise there. That's the premise of the chapter, and that's what we talked about in 9.1. Okay, so that's what you need to know for 9.1. 9.2 is when we started talking about quadratic inequalities in one variable. So if we have what looks to be a function, or I don't want to call it an equation, but a function or a relation here, and we just have one variable involved in this whole inequality, and the other side is equal to a constant or 0, that's one variable. And in this case, we're looking for the x values that cause the inequality to be true. So we're not looking for points. There are no solution regions, shaded regions, when we have one variable. We only have the solution regions when we have two variables. Notice x and y in the previous example. That's when we have shaded regions. If we just have one, what we're looking for is we're trying to identify the x values. So you look at the x-axis and you try and identify x values that satisfy the inequality. So again, what we want to do here, let's take a look at this one right here. X squared minus 3x minus 4, that's the That's this parabola here that we've graphed, okay? And where are the x values that cause this parabola to be less than 0? And the parabola being less than 0, that's the y values, okay? So here are the negative y values on the coordinate plane there. And so the graph here is negative, and I'm outlining where the graph is below the x-axis or where it has negative y values associated with it. So I'm going to zoom in here now, and the x values that we're looking for this inequality right here would be the x values that are between -1 and this intercept of 4. You see there? So it's a little bit tough to maybe see, but okay, so where the graph is negative, we're looking for those x values that are associated with that negative part of the graph. So these x values give these y values down here, or this graph down here. So for this one, we're talking about the x values between -1 and 4, looks like. And if we're talking about where the parabola is greater than 0, that means we're looking for the x values that are associated with the graph where it has a positive y value. So that's this part of the graph and this part of the graph. That's where the graph is positive, where it's above the x-axis. Okay? And so the x values that are associated there are everything less than -1, because those yield the y values that we see up in here in the graph. And all of the x values that are greater than +4, because those yield these y values. So for this one, so let's write out the solutions here. So for the greater, this one here, this red one that we just identified here, the solution set would be, okay, x values less than -1 and x values greater than 4. And notice, because this inequality does not have an or equal to, we are not putting an or equal to in these inequalities in the solution set, because we don't want to include the 0. And then for this blue one over here, the less than, so that was the solution set for the less than, is everything between -1 and 4. So I would put -1 here, I would put 4 on the other end, I'd put the x in the middle, and then this would be a less than sign here and here. This means, this is the, what is this, the set notation, I guess. This means all x values between -1 and 4, but not including -1 and not including +4. Okay? So this one is attached with the less than, and this red one is attached with the greater than. Any questions? Okay, and I think students have most trouble with this section, to be honest with you. I've had more questions about this than the shaded regions. All right, now part 2 is how to solve for these inequalities algebraically, and there are 2 methods we're going to use. One is using roots and test points, and the other is called Sine Analysis. All right, so we're going to talk about both of those here. And so in order to solve an inequality like this without necessarily graphing it first, okay, what you do is you want to find the roots or factor and find the zeros. Once you've found the zeros, what you notice is that the x values, the domain, is now split into different sections. So the roots, -1, that would be a split point on the x line, and +3 here would be another split point. And what I mean by that is, if we were graphing it, it probably would look something like this, right? This is what the graph would look like. And so probably, because it opens upward here. And so probably we know kind of what's happening here, but algebraically, without using the graph, we would use test points and use a point from each of the 3 sections. 1, 2, and 3. So down below here, I've shown you how I've done that. So a test point in this first section would be -2, let's say. I tested this point. And you would literally plug it into this inequality. Wherever you see x, you plug in -2. Once we evaluate that, I have 5 on this side, and I have obviously 0 on the right side. So you would ask yourself, is 5 less than or equal to 0? Does that satisfy the inequality? And the answer is no. So that means that the x values over here do not satisfy the inequality. Now I would test a point from this second section here between -1 and 3. And as you see here, -4 is less than or equal to 0. So we have a success here. It looks like our solution region is going to be in here. And of course, finally, we test the number 5 in this region, and that doesn't work either. So that's where we come up with our solution set as x values between -1 and 3. Now, this is an or equal to as well. So we have to make sure that these signs are less than or equal to on either side of the x. All right. Any questions there? So you have to factor your expression, find the roots, and then use test points for those sections. Okay. Here's the second method of solving algebraically, and this is using sine analysis. So is this the exact same? Yeah, this is the exact same question. So sine analysis is a fairly new concept for you guys. And so this is how we use sine analysis. We still have to factor. Okay, so it's very similar to finding the zeros and using test points, but instead we're going to have to factor this. So factoring a quadratic into two binomials, x is going to go there and there, and we're going to go -3 plus 1. Looks like because -3 times 1 is -3, and -3 plus 1 is -2. So that is the factored form. And sine analysis, what we do is we're going to write each factor on the sort of left side of this kind of elongated L here, and you're going to list the factors just as they appear on the left here. And what we're going to do is we're going to analyze where each of these factors is positive, negative, or 0. And we're going to use the row. We're going to use the horizontal row to list those signs. And where we always start is we always start with where is each factor equal to 0. And down here, you'll notice I have two little arrows here. This is the number line. So that's representing the number line. So x minus 3 is 0 when x is positive 3. So I'm going to put positive 3 on my number line right about here. And right above positive 3, I'm going to put a 0 in line in the same row as this factor. Okay, so that's in the same horizontal row as this factor. So x minus 3 is 0 at x equals 3. Now, if x was less than 3, what is the sign, S-I-G-N, of this factor? Are all those values positive or negative? And you could do a test value, so it's very similar to the last method. But if you think about something that's, 0 is less than 3. So 0 minus 3 is -3. So all of the values of x less than 3 make this factor negative here. And that's the beginning of sine analysis. We're going to analyze the sign for each factor. And obviously if x is greater than 3, like 100, 100 minus 3 is obviously a positive number, so it's positive on that side. Okay, any questions about that first step there, sine analysis? Okay. Good thing is we do the exact same thing to the second factor. So at x equals -1 is where this factor is 0. So in the same row, I put a 0 here. And is it positive or negative? And which side? So any x value is less than -1, like -100, this whole thing, this expression is going to be negative. So I put negative signs there and positive signs on the right side. And yes, most times, as long as the x term, this is a little hint, as long as the x term is positive in these factors, then yeah, you're going to have negative on the left of 0 and positive on the right. Still, you should check each time. But if you have, if this is not squared, or if this whole thing is not squared or whatever, that's the general pattern, okay? So basic sine analysis is usually going to have negatives on the left of the 0 and positives on the right. But this is not the point. The point is, what is the function doing? So what is the sign of the function? Remember, because this f of x right here, we're treating this as sort of a function, and we want to know where this whole thing is 0 or negative, right? And so once we actually multiply, kind of a mock multiplication, I can see what the overall expression or function is going to be. So in this region of the domain, this factor is negative, and this factor is also negative with any x values less than 1, negative 1. So guess what? When you multiply those together, the function is actually going to be positive. Now what happens at negative 1? Well, we have a negative number times 0. So that's going to be 0. The function will be 0 at that point. And that makes sense. That's an x-intercept. Here we have negative value times a positive. So the signs are different for these x values. And when you multiply those, you get a negative value. So a negative times a positive is negative. At x equals 3, we have, again, 0 times. Well, 0 times a regular old number is always 0. And then finally, positive times positive gives you a positive. And this should match up pretty well with the previous example. Okay, so this was, let's see, this is positive. This yield positive results here. This was negative here, and this was positive results here. Okay, see positive, negative, positive for our examples. And of course, with the graph, positive here, negative here, positive over here. So positive, negative, positive. And that's matching up here on the sign analysis as well. Positive, negative, positive. So the solution set, where is it negative or 0? You're looking for the x values between and including negative 1 and 3. So we write that as negative 1 less than or equal to x less than or equal to 3. Okay, any questions there about the sign analysis? All right, so make sure you're able to do that for your test coming up. Now, this is the last section in the chapter, so we're almost done. And this is actually very similar to the first section when we're talking about now the solution regions. Except what we're talking about now is we're getting into quadratics. Okay, so just as a refresher, and again, I won't spend too much time on this, but this is from 9.1, and we can identify the inequality here by naming the boundary line and then looking at the dashed or solid nature of this boundary, and then using a test point in the solution region to confirm our inequality. So I'm going to do this again because this is a different type of problem that we've done on this review. We haven't done this one quite yet. So in order to identify this inequality, we know that this is a line, and I can see that the y-intercept is negative 4. So I'm going to think about y equals mx plus b is the nature of the line for our boundary. And b is negative 4. I know that. What's the slope? Well, the slope, I want to pick a point like this one and another point that I know for sure that this travels through. And it looks like 2, negative 1 is another point. So I'm going to calculate the slope. This has a rise of 1, 2, 3, a rise of 3, and a run of 1, 2. So it appears that we have a slope of 3 over 2. And if I go 1, 2, 3, 1, 2, look at that, I hit another point, and that seems to pan out. So my equation for this boundary line is going to be y equals 3 over 2 x minus 4. Everyone see that? Now we're not done because this is an equation and I don't want an equation. Instead, I want to change this equation to an inequality that is satisfied by all the points that are shaded. So I always hint, use 0, 0 as a test because that's always easy to do. So here's 0, 0, and you know what? That's part of our solution region. So when I test 0 for x and 0 for y, and I'm going to show that right now, I'm going to put the appropriate inequality in here. So 0 is what compared to negative 4? 0 is what compared to negative 4? Well, 0 is bigger than negative 4 because it's to the right on the number line. So 0 is actually bigger than negative 4. 0, 0 is in the solution region, so this is the inequality that I should use. The line is dashed, so remember, if the line is dashed, the boundary line, then it's not or equal to. So here's the dashed. You do not put the or equal to if it's a dashed line. So all in all, my inequality here is y is greater than 3 over 2x minus 4. So that appears to be the inequality for this system of, or not system, but this inequality here. Okay, linear inequality. Now, in 9.3, we're talking about the same concept, but with parabolas. So instead of graphing a line, we graph a parabola. Instead of looking at trying to find the equation of the line, we look for finding the equation of the parabola. Everything is exactly the same other than that. So here is the inequality for a parabola. Notice that we have a parabola, a quadratic here. I have an inequality, so I'm going to be shading because I have two variables. So this is in two variables. That's important as well, because we just got finished talking about what happens with one variable. So two variables means we shade a region. We need to have x and y coordinates of points that are satisfying this. So identifying the parabola here, you use the vertex is a good idea, intercepts, or other known points to find a value and such. This one is given to you, and so we can connect this with this graph. So 0, 0 is not in the solution region, so that means 0, 0 shouldn't satisfy this inequality. Let's just test that out. So this should not be true, what I'm writing here now. Okay? This should not be true. Let's see. 0 is less than negative 3. Well, 0 is actually greater than negative 3, so that is not part of the solution region. So we've confirmed that. Okay? And that's what I did here, checking with a test point. Okay, this is a question that you'll see, write an inequality that describes this graph. Well, here's the boundary equation that they've given to you. That's nice. And all you have to do is put the proper sign in here, okay? So you have to basically take away the equal sign and put in the proper sign. And here's where you just use a test point. 0, 0 should make this equality true. I've tested 0, 0, and I have 0 is compared to 5. How? Well, 0 is less than 5. So this equation now becomes a less than statement. Okay? Again, start with the equation, do a test point, put in the appropriate inequality sign. Okay, you guys good so far there? All right, I am going to do one more example, just one more example here on how to label a inequality when you're not given the expression, okay? All right, so here's the final example that I'll do for this review here. This is a question where you're given a graph of an inequality, and obviously it's going to be in two variables because we have a shaded region here. And so what I need to do is identify the parabola, and then I need to use a test point to confirm the inequality sign, okay? So the biggest thing is probably identifying the parabola here. That's probably the toughest part. So let's use the vertex graphing form maybe. So I have y equals, and again I'm just using the boundary line, so we'll just show an equals there. And this is the format, right? Oh, you don't, sorry, do you guys use P? Yeah, you guys use P. Then plus Q, okay? So the vertex is 1, what is that? 3? 1, 2, 3? 1, 3. So we have y equals a, that's x minus 1 squared plus 3, right? 1, 3, okay? We have that so far. Now what we need to do is find a. So we know that a, you go over 1 unit from the vertex and then either up or down a units. Now this is too hard to tell. We cannot guess. That looks like maybe a third, I don't know, maybe close to a half. It's really tough to tell. So what we need to do then is we need to do one of two things. We can use one of the 2 points that are given, and this is a point that's clearly given, and I can put that coordinate in for x and for y and solve for a. Because these are intercepts that are given, you could also set this up another way. You could do this, y equals a times x plus 2 for this intercept, and then this intercept would give us an x minus 4. So you could start either way using the vertex form or using kind of the standard form, but you still have to plug in another point and solve for a somehow. So I'm going to continue on. I'm just going to leave this one alone for now. I'm going to continue on with my first method, and I'm going to use the point 4, 0, and I'm going to put 4 in for x here. I'm going to put 0 in for y, and then I'm going to solve for a. And that'll be the final piece of the equation part of the boundary, okay? So I've got 0 equals a times 4 minus 1 is 3 squared is 9. Okay, so I've got negative 3 equals a times 9. Divide both sides by 9. It looks like I'm going to have a equals negative 1/3. Okay, so we guessed about a 1/3 for a, and of course it's in the down direction, so it's negative 1/3. So here's my equation for my boundary. Y equals negative 1/3 x minus 1 squared plus 3. Good? Question? I know I'm going kind of fast, but this is review. So now what I need to do, and this is the easy part I guess now, is I need to pick a point that's in the shaded region. That's what I'm going to do. I know you could use 0, 0, but I'm going to pick a point that's in the shaded region, and then I'm going to put the correct inequality symbol in there so I don't mess myself up. So what I'm going to do is I'm going to put in the point 6, 0. See that? 6, 0 is definitely in the solution region. So I'm going to put a 6 here. I'm going to put a 0 here. I'm going to evaluate both sides, and I'm going to put the correct inequality in. So let's see what that looks like here. Well, I've got 0 equals negative 1/3 times 5 squared plus 3. So 0, now I'm going to get rid of that equal sign, I guess. 0 compares to this side how? This is negative 25 over 3 plus 3. Okay? So 0 is compared to, so what's this 3? Negative 25 plus 9. 16 over 3. Negative 16 over 3, let's say. If this is actually 9 over 3. Negative 25 plus 9, negative 16 all over 3. So 0 is clearly greater than a negative number. See that? 0 is greater than a negative number. And because this line is dashed, I do not put the or equal sign. So I am pretty much done now. I've got y is greater than negative 1/3 times x minus 1 squared plus 3. And I believe, someone can double check this for me, I believe that this should be the answer for this question. I think this is 8b in 9.3 if you want to check. Can anyone double check that for me? You guys are following along here? Let's just double check that. All right, so that is confirmed. This is the inequality here for this question, and that concludes the review. So chapter 9 review, couple things to remember, please. If we have two variables, we're looking for shaded regions, whether the boundaries are linear or quadratic. If we have one variable, we're looking for only x values, and that is the x values on the sort of the number line or on the x-axis, just the x values, not points. There's no shaded regions when we have one variable. And yeah, sine analysis. Please be aware of sine analysis. Need to know how to do that. That's important for the rest of pre-calculus 30 and calculus. This is something that's really important. Okay, quadratics in two variables. Okay, there you go.